All right, so I'm going to do the same thing with this new example. I have a new region. I've been given a graph, so that's nice. Sometimes we'll have to make our own graph, but I've been given a graph, and this is the problem from your textbook. I've been told the upper boundary of that graph is x plus x cosine x. And I know I'm supposed to go between x values of -2 and +2. I've also been told I'm going to revolve that area around the x-axis. So it's not always the x-axis, but we'll talk about that later. For now, it's the x-axis. So I'm going to try those same steps. I'm going to scooch my picture out of the way. And can I encourage you to try to use those same steps that we talked about before? So I'm going to make my region is already shaded. Maybe I want to label it R. I'm going to color in my axis of revolution. I've been told I'm going to revolve around the x-axis. I'm going to color that red. I'm going to revolve my region across the axis of revolution. So no easy feat, but doesn't have to be perfect. So there's my reflection of R. Now what am I going to do? I'm going to, well, stop and notice. Probably should have stopped and noticed in that first example. Everywhere I try to draw in a vertical line between x is -2 and x is +2, I always have the same curve forming the top boundary and the same curve forming the bottom boundary. So I don't have to worry about breaking up this integral. You might see some more complicated pictures, but for now, know that I have one boundary. I'm gonna be fine. I don't have to split up my integral. So my next suggestion was that we draw in a slice. So I'm going to start my slice on the axis of revolution. I'm going to draw toward the function I know a function for, draw toward the boundary that I know a function for. So just to clarify what I mean, this is one boundary I might hit, and I know that function, that's f. I could have drawn the other direction, but I'd get to this boundary, and nobody gave me an equation for that. So you don't want to mess with something you don't try to aim for a boundary you don't have an equation for, because then you have to stop and figure out the equation for it. Especially since you have one that we do have an equation for. So we're going to aim for that boundary that was already drawn in the original picture. And we're going to draw back behind the axis of revolution and come back to where we start. So this is what I'm going to draw. I'm going to start here on the axis of revolution, draw toward my f of x. Pretend I'm drawing back behind the axis of revolution and back up to where I started. If you want to draw in more slices so you kind of get the hang of it, I'm going to draw here, back behind, and come up to where I started. Now I'm going to draw in a blue radius to my slice. The radius should start at the axis of revolution. You could start on a point in the circle too, but I want you to form this habit so that when it's the AP test and you're nervous, your habit will kick in and you'll be in good shape. So I'm going to start at the center of that circle. It's not really a circle because it's a circle with thickness, but we're going to treat it like a circle for now. Oh, that one's tricky to draw. Okay, so you can see my green slice went a little high, but I can tell that what I meant, and that's that my blue radius is going to bump into f of x at the top. And my blue radius bumps into the axis of revolution at the bottom. So just like the last example, my blue radius is vertical. So I would find the distance for my radius by subtracting top curve minus bottom curve, in this case f of x minus 0. So now I can write an integral. I've been told the axis of revolution is the y-axis, so I know I'm going to need to take my slices perpendicular to the x-axis, which means the thickness of my slice is a very small change in x. Now, obviously, you sometimes paint yourself into a corner if that's the first part of your integral you write, but you'll probably not mess up the variable, so you can choose what you want to do. But I like to write that first so I know I'm not messing up the variable, because now I know I have to write my integral in terms of x. So I'm going to put x limits on it. That has to be from -2 to +2. This is a case where I was given the limits at the beginning. Sometimes you'll have to stop and figure them out. and I know I'm supposed to integrate area, the area of the face of a slice. If I could take that green disc out and look at it, it would look on the face like a cylinder, but it has a thickness. So I need the area for that circle. Area for circle, pi r squared. Pi r squared. Well, what's my expression for r? I said my blue line is bounded on the top by f of x and below by the x-axis, which is y equals 0. So I'm going to write, well, in the AP test, feel free to write f of x there. When you have to actually evaluate this integral, you'll have to type in the correct expression for f of x. But that's probably worth 2 points on the AP test if you could write that, and then a 3rd point for correctly plugging it into your calculator and computing a result. Which you can see in your textbook says is approximately 52.43 cubic units. But again, I know you know how to type an integral into a calculator. My goal is to make sure you can write this integral. So notice x limits on an x integral because I've taken slices that are perpendicular to a horizontal line, so my slices are vertically oriented, which means their thickness is a small change in x. And then area for a cylinder, or area for a circle, pi r squared. Here we go, here's the lampshade problem. I've been given a curve. This is interesting. This time I was given the curve x as a function of y, which is not typical. But this to help me sort of make that transition. On the AP test, they're probably not going to tell you, but here we're going to, help you out in your first couple of problems here. So you're probably already wondering what's up when I give x as a function of y instead of y as a function of x. But you can see the curve. It's the blue curve over here on the right. And I've been given boundaries, like it's a range, right? Because it's limits on the y value. But I've been told that y comes between +1 and 4. Happy 6th period. And this time I've been told I'm going to take that region and revolve it around the y-axis. So here I might not do all of those steps just because I already have this picture and there's this fly. But notice that this is the region that I'm going to revolve. And you can see this picture already has the revolving done for me, which is nice. So I'm going to call this, if this was R, this is the reflection of R. And you can kind of see there's the start of a green disc is drawn in there. I'm going to go through the rest of the steps though and see if this can help me. I'm going to revolve around the y-axis. So I'm going to draw that in as red. I'm going to try to draw a slice. I'm going to use my green marker. I'm going to start at the axis of revolution. I'm going to draw toward the function I know. I don't know that function. Obviously I can figure it out. But this one I have an equation for, so I may as well use it. Because I'm going to need to know some kind of expression, some kind of equation for my radius. So start with a function I know. I'm going to draw from the axis of revolution toward the function I know, back around behind the axis of revolution, and back to where I started. Was it a great slice? It wasn't a great slice. So if you want to do it again, cool. So here's my slice. Maybe you find sound effects help. And now I'm going to draw in the blue radius. I'm going to start at the axis of revolution and draw toward the edge of that green slice, ideally running into a function whose equation I know. In this case, I can see I've run into x equals 1 over square root of y. So now that I've drawn the blue radius, I might try to write an expression for the length of that blue line segment. Notice this line segment is horizontal, which means if I want to find its length, I have to subtract 2 x values. Because if I tried to write the ordered pair for those 2 endpoints, they would have the same y value. That's not gonna, the y's don't contribute to the distance of a horizontal line segment. So I would subtract x minus x. I would ideally subtract furthest right x minus furthest left x so that my result would be a positive number. So I noticed that on the right-hand side, I bumped into, if I'm supposed to subtract like x2 minus x1, on the right-hand side, my x was 1 over square root of y. And on the right, my x was whatever the x is on the y-axis, but on the y-axis, x equals 0. So that's my radius. Now that I have an expression for my radius, I'm going to write my integral. I have an axis of revolution that is vertical, which means I'm going to take slices that are horizontal. And if you look at this slice and try to figure out how thick it is, it's a very small change in the y values. So I'm going to fill in my infinitesimal, my dy. I know I'm going to have to integrate now with respect to y, which means I'm going to put y limits on this integral. This is going to go from 1 to 4. Whoops. 1 to 4. And still pi r squared. So pi times radius squared. So this is, I'm integrating area times thickness to model adding up infinitely many volumes of infinitely many very short, very thin cylinders. So my r is going to be 1 over square root of y. I could have put in 1 over square root of y minus 0, but feel free to simplify now. Because it's about to get a little crazy, I'm going to have to integrate here, and I haven't given myself much room. That's going to be the integral from 1 to 4 of pi times 1 over square root of y squared is 1 over y dy. I'm going to jump up here to integrate. The antiderivative of 1 over y is natural log of absolute value of y. Of course, I could have left the absolute value bars off because my y's go from positive 1 to positive 4, so there's nothing to take the absolute value of, right? I'm going to multiply by pi, and I'm going to evaluate from 1 to 4. So that's pi times the natural log of 4 minus natural log of 1, which is pi times the natural log of 4. There you go.